All right.
All right, Emma, go right ahead.
Thank you. I just wanted to announce that well, I'm sure you guys know there's several other SIs for, especially for Okame. My bad, I'm getting ahead of myself. Um, well, we agreed that maybe it would be more beneficial for all sections to have access to all three of the SIs. That is me, Justin, and Grace. Grace is the SI for Professor Cody's section. So all the information will be on my Padlet. My Padlet link is on the homepage. Um, the only thing is, just a little fair warning, is that they are a couple lectures ahead. So just try to keep track of, like, you can see on Grace's Padlet their schedule and what they're covering in both SI and their lecture. That way you guys have a better idea if you guys want to attend one of her SIs. But other than that, you guys can attend either mine, Justin's, or Grace's. It doesn't matter, but you really are at that point in the semester that I feel that a lot of students started to feel a little bit behind. So I really suggest, getting that extra practice in, and SI is a really good way to do that. So that's really it. You guys have options. Just know that, and you guys can contact me for questions.
Emma, do you know Grace's last name?
Yes, Grace Chen.
Chen. Okay. I was just going to reach out to her so I could put her info out on Canvas as well.
Sounds good. All
Okay.
right.
All right. Thanks. Any questions for Emma? Okay. Yeah, and you know what? I'll reach out to Cody also just to kind of see where he's at in his schedule, because I know you said that he's a couple lectures ahead of us. Let's see, Cody's schedule. So I'll just kind of see when it looks like we're going to get caught up, just to kind of give you guys all a heads up.
Yeah, it should be fairly soon, in the next couple of weeks.
Okay. 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 So we are going to continue with chapter 7 today. Oh, I lost Zoom. Where did it go? There it is. Sometimes I feel like my mom when I say things like that. I've had multiple conversations with my mom while we've both been on our cell phones. And she'll tell me that she has to hang up because she can't find her phone. And it's obviously in her hand. There we go. Well, too far. All right. Last time we talked about 2 of our reactions. And if you remember, I said that we're going to talk about 4 main reactions. There's going to be about 4 others towards the end that we're going to talk about in a lot less detail, but we're going to do 4 main ones. So we've done SN2. So that was our substitution reaction. It has a 2 there because there's 2 things happening at once, a nucleophilic attack and the loss of a leaving group. And then last time we ended with E2, which is an elimination reaction where there's 2 things happening at once. So there's a loss of a leaving group and a proton transfer happening all at once. So where we're starting today is actually looking at alkenes. So every time we do an elimination reaction, we're going to form an alkene. So we're actually going to talk about how to name them, and then a little bit about stability, because one of the things, it's on here somewhere, down here, one of the things that we talked about with the E2 reactions is that the most stable alkene is going to be our major product. But we don't know what that means yet. We don't know what makes an alkene more or less stable. So that's going to come up real early today. So we're going to start with nomenclature though. So last time we learned how to name alkanes that have halogens on them. Today, we're adding in alkenes. And so just like before, same rules. We want to have the longest parent chain. We want to use low numbers. We want to alphabetize. Here's where we're going to add to those rules in order to name our alkenes. And this first one is actually a good thing. The parent chain needs to include that carbon-carbon double bond. So as we start to learn functional groups, so we have our carbon-carbon double bond, we're going to have carbon-carbon triple bonds, alkynes, coming up very soon as well. when we have a functional group, it needs to be in the parent chain. So the example that's down here, if we just look at that long chain right there, that's 8 carbons, but it doesn't include that double bond. So we're going to use the 7 carbon chain, even though it's a little bit shorter, because it has to include that functional group. So we can even amend our statement up here, number the longest parent chain that includes the functional group. And I think that's even how I have it written in future chapters. Here's another thing that's good. And I say that these are both good because it lowers the options. So like one of the questions you had on the test was kind of a crazy alkane and you had to figure out where that longest chain was. Well, if there's a double bond in there, you know that it has to include that portion. So it eliminates a lot of possibilities. So the second thing is that the carbon-carbon double bond gets the lowest number. So we don't have to figure out if we want to number it from left to right. We just look at where that double bond is, and we're going to number from the side it's closest to. So again, we're giving that functional group priority over everything else. When we're naming it, the parent chain is going to end in -ene. So just like alkanes ended in -ane, alkenes end in -ene. And then in the very front, cis, trans, E or Z, if needed, to give it that extra information about stereochemistry. Okay, we are going to practice this on the next slide, but any questions? Okay. Let me draw a couple for us then. There's one. Let's try that again. Oh, I know what we need. Let's try to think. Oh, gosh, start that again. Okay. We need one with 2 double bonds in it. All right, on that first one, where should we start numbering it?
The carbon to the left.
All right. So 1, 2, 3, 4, 5. We're not going to keep going that way because that would just get us to 6. So we're going to go 6, 7, 8. Okay, so we have a substituent there. We have a substituent there. We have our double bond. We do have a couple chiral centers. Carbon 2 and 5 both are chiral centers, but we're not given any dashes or wedges, so we can't figure out if there are S, so we don't need to include that. We do need to look at the stereochemistry of our double bond, though. So what's going to go in the very, very front of our name?
Chloro, 2-chloro.
2-chloro. What comes next?
5-methyl.
Good. In stereo, I love it. Okay, here's where our new stuff comes in. So we have an 8-carbon chain. What is the name of our parent chain now that it has a double bond in it?
Octene.
Very good. And so we have to put a number to say where that double bond is. And so we're always going to put the lower number. So the double bond is between carbons 3 and 4, but we only need to put number 3. So we're going to say 3-octene. And so when we see that, if we like, let me go back one here. When, oh, that one's not numbered, never mind. When we see it written as 3-octene, we always know that that's going to be between carbons 3 and 4. If it was written as 5-decene, we know it's going to be between carbons 5 and 6. So the number is always the lower number of the double bond. We're missing a little bit of stereochemistry. What am I going to put in the very front for that double bond? Would we label that double bond as cis, trans, E, or Z?
Cis, trans.
Trans, good. So let me switch colors and I'll show you why it's trans in case you don't see that. So I'm going to fill in my hydrogens here. And that's why we can label it as trans, is because we have a hydrogen on each carbon and they're opposites from each other. They're on opposite sides of the double bond. All right, questions on that first one? Okay. What about this second one? So we know what our parent chain is. And I say that with certainty because this structure contains 2 double bonds, and both of those double bonds need to be in the parent chain. So that has to be my parent chain because it contains both of the double bonds. So we already know we're going to have this propyl substituent. But for that parent chain, should I start numbering it on that bottom portion or that far left portion?
Bottom.
The bottom.
Yeah, I agree. 1, 2, 3. And so we can double check. So if we do that, our double bonds would be at 2 and 5. If we numbered it the other way, 1, 2, 3, 4, 5, it would be at 3 and 6. So it's definitely lower this way. All right, so I already said it's propyl, so we'll start there. We'll start with 4-propyl. Actually, give myself a little more space there. 4-propyl. All right, we have a double bond at carbon 2 and at carbon 5. It's another 8-carbon chain, not on purpose. So if there weren't any double bonds, it would be octane. If there's one double bond, it's octene. Any guesses as to what we're going to call this with 2 double bonds? How do we put in the 2 into that?
Octadiene.
It is octadiene. So we're going to do 2, 5 octadiene. So notice the A comes back from octane, and that's really just to make it easier to say because it would be harder to say octadiene, or it makes it sound like it's 2 words. So putting the A in there just makes it a little bit more normal. But so octadiene. So if we look at that word, we kind of break it down. The octa is because we have 8 carbons. The ene is because we have a double bond, and the di is because there's 2 double bonds. Questions about that name? And we could, go ahead.
Oh, do we need to put the trans?
Yes, and so that's actually what I was going to ask next. So let's see I think everything is trans, isn't it? So the way we would do this, let's see, I'm going to erase this circle, just get out of my way here. We have to put both. So just like if it was chiral centers, we would put 3R, 7S, whatever it might be. We're doing the same here. So we would do 2 trans, 5 trans, parentheses, dash, and then the rest of the name. If we also had a stereo center, like if we had a wedge here with a chlorine on it, so that would be an R, then we would also have 2 trans, 5 trans, 7R, and they would just all be in that little parentheses in the beginning. It's just our little stereochemistry section of the name.
I have a quick question.
Yeah.
When we're deciding the lowest number for like the substituents,
Mhm.
does the double carbon take priority over other substituents?
Yes, it does.
Okay.
Yep. And that's going to be true for all the functional groups that we look at. And then eventually we're going to have structures that will have more than one functional group. And there's a list of priorities for those as well. So it actually makes naming easier because it means that you have less decisions to make because there's a rule for it.
Okay, thanks.
You're welcome. Anything else on the names here?
What would happen if the propyl had a double bond on it?
Oh, that is a good question. So then we would 4, 5, 6, 7. So it would still be the substituent because that 8 carbon chain would be longer than if we were to include the propyl group with either portion. And so we have to add in the ene to the end of it. So it would be a propylene would be the name of it. I don't ever give you ones like that, but that's a good question.
Okay, thank you.
You're welcome. Anything else? Okay. All right, stability. We have a couple things to talk about with stability. The first one, though, trans is more stable than cis. So if we have a trans double bond versus a cis double bond, any thoughts, any ideas on why that trans double bond is going to be the more stable one? It's a reason that we've used for other things, if that helps. Yeah, that's exactly why. So Jada put in the chat. So it's steric strain or steric hindrance. So when we have a cis double bond, so depending on what's attached right here, so I just drew the smallest trans and cis double bonds possible. But if those were bigger groups, there's possibilities that they're going to run into each other. And so when we're in that trans configuration, that's not a possibility. The big groups are far away from each other. So our reasoning here, why? Steric hindrance. Told you, if you don't know the answer, that's our go-to answer in those classes, steric hindrance. Within the trans grouping though, we can further rank things. And so we have a list down here on the bottom of stability. Monosubstituted is our least stable. So let's add some words up here. Least stable to most stable. And on this list, we're going from how many substituents are attached to the vinylic carbons. So remember, the vinylic carbons are the ones in the double bond. So how many substituents are on those carbons? So we're going from mono to di to tri to tetra. So our cis and trans argument would be right in here. Let's see, let's put them in order. Cis and then trans. So the cis and trans is just kind of a small portion of the stability because we can really only use cis and trans if there's 2 substituents. And then outside of that, it's based off of numbers of substituents. So it's more stable when we have more substituents because it's helping to delocalize electrons. So we've heard that reasoning a few times before. In the middle of the reaction, as things are moving around and we're losing a hydrogen, we're losing a leaving group, our carbons are going to become partially charged, partially positively charged. And so they aren't technically carbocations. Sometimes they get referred to as pseudo carbocations, which is like the way to say fake carbocations. It just means that they're going to have a partial positive charge that's pretty strong. And having those extra substituents is going to make them more stable. So, short story here, to turn this long story into a short story. An alkene is going to be more stable when it has more substituents, and it's going to be more stable when the big substituents are far away from each other. So even if it's tetrasubstituted and we have like a methyl and we have like a cyclohexane over here and and another methyl over here and a big chain over here, because we have the two big groups next to each other, that's going to be less stable than having this big group and this big group trans from one another or opposite from one another. So we want to have as many groups as possible, and we want to have the two biggest groups opposite from each other. That's what's going to make an alkene as stable as possible. And so we're talking about this because as we do these reactions, the most stable alkene is going to be our major product. And so we have to decide, well, is the double bond going to form on this beta carbon or on this beta carbon? And so we can look at this as our reasoning. More substituents, trans configuration. A little bit more on alkenes and rings and cis and trans. So if we have a ring that contains a double bond, if it contains 6 carbons or less, it can only be in the cis configuration. So if we look at one of these double bonds, the hydrogens are on the same side of the double bond because that double bond is within the ring. So it's in that cis configuration. But if we have 7 or more carbons, there's enough flexibility in the ring that we can actually have a trans double bond. And so in the name, we would have to state if it's cis or trans based off of what it looks like. Okay, so back to our reaction and back to alkene stability. So on that first slide of E2 reactions, I had introduced a new word to us, this one right here, regioselective. And so as we talk about reactions, we'll talk about their stereoselectivity, meaning is it going to keep the same stereochemistry or is it going to be the opposite? So we talked about that with SN2. And then with reactions, we talk about regioselectivity. And that means if the reaction can happen in more than one location, which one is preferred? So this is the official definition. If more than one product is formed, one of them is major. So that's telling us that this is a regioselective reaction. And one kind of side note on that, that means that if more than one product is formed, but if they happen, but let's try that again. But if they form in equal amounts, then it's not a regioselective reaction because it's not selecting one side over the other. So saying that it's regioselective means that it's selecting one region or one area over the other. So kind of a little, just to make sure we understand the wording there. All right. Let's look at the reaction up at the top, and then we'll use the language in the bullet points to kind of explain what's happening. So we have 2-bromobutane as our starting material. We're reacting it with this guy. So the name of this is methoxide. Just putting that there because I'll probably use its name. We're using this because it's our base. So in this reaction, if you remember back to our E2, 2 things are going to happen at the same time. Bromine's our leaving group. It's going to leave. The base's job is to remove a hydrogen from the beta carbon. So right here, it's telling us that there's 2 beta carbons. So remember, the carbon where the halogen is attached is the alpha carbon. My little tiny alpha symbol, not very pretty, but it's there. And so the carbons next to it are beta carbons. So we're saying that the base can remove a hydrogen from the beta carbon on the left, which would give us this product. So this is our left beta carbon. Or the base can remove a hydrogen from the beta carbon on the right, which would give us this product. So let's see, let me grab a different color here. So this carbon right here, So it's carbon number 2 if we're numbering it, but that's our alpha carbon. And so the alpha carbon is part of that double bond, no matter what. We're just saying, is the alpha carbon going to form a double bond on its left side or on its right side? And underneath that, oh, let's talk about these real quick too. So this is just the conjugate acid of the base that we started with. So that's our methoxide with the hydrogen it grabbed onto, and that's our leaving group. So just to give everybody an explanation. Okay, underneath the alkenes, we have some percentages, 20% and 80%. That's telling us that 80% of the product that was made was 2-butene, or it formed because the hydrogen was removed from the beta carbon on the right. And 20% of the product is 1-butene, and it was formed when we removed a hydrogen from the beta carbon on the left. Our reasoning is because our major product is the more substituted alkene. So I'm going to draw out those two, just because sometimes when they're written that way, it makes it a little bit harder to see. But that's our 2-butene. And that's 1-butene. When we're talking about numbers of substituents, butene has 2. It's a di-substituted alkene. 1-butene only has 1. The hydrogens don't count when we're talking about substituents. There's always going to be hydrogens. The hydrogens don't make an impact in terms of electron delocalization, carbocation stability. So we don't count those in any way. This is a mono substituted alkene. So our 2-butene is going to be more stable because it's more substituted. It gets a special name. It's called the Zaitsev product. So this is named after the guy, Zaitsev, who figured this out. But Zaitsev's rule says that if we remove the hydrogen from the beta carbon with less hydrogens, we'll get the major product. So if we go back, I'm going to do a little erasing on my starting material over here, just because it got a little busy. But if we go back and look at our 2 beta carbons, one of them has 3 hydrogens, and the other one has 2 hydrogens. So Zaitsev's rule says that if we take a hydrogen from the beta carbon that already has less hydrogens, then we'll get the major product. So that gives us our major product. And so the reasoning there, if it already has less hydrogens, that means it has more carbons attached to it. So it's going to have more substituents. So Zaitsev's rules is just kind of a way to help remember how to get us from that starting material to our product. There has to be a name for the other guy though, right? So let's see this one. This is our Zaitsev product. The other one, the minor product, which is our less substituted alkene, is called the Hoffman product. And we do use those names a lot. We'll refer to them as a Zaitsev product or a Hoffman product as a way to say that it's the more substituted or the less substituted product. I don't use a lot of the names like that, but these ones are honestly too ingrained in the book for us not to use them. The percentages here are telling us that this is our major product and this is our minor product. So it's based off of quantity that we're making. We're gonna practice this on the next slide. I'd make sure it was my blank one. Before we do a practice one though, do we have questions? My nose is itchy. Okay. Okay, let me see. I think I have 2. Nope, I just have 1 blank slide. I have a few practice problems here. Oh. Okay. Okay. I just put them all at once, but we're not ready for a couple of them.
I had a quick question. How did we determine it was the beta carbon again?
Oh, I'll label on this one. I'll show you.
Oh, okay. Thank you.
Okay. So here's our reaction. We have this carbon chain with a bromine attached to it. We're going to react it with some base, and we're going to draw all, and actually I'm going to be a little bit more specific on this one. We're going to say we're going to draw all of the E2 products, and we're going to circle the major product. All right, so to answer the beta question, where the halogen is attached, that's our alpha carbon. And so the carbons attached to that are the beta carbons. So there's a beta carbon and there's a beta carbon. So we have 2 beta carbons to choose from as we do this. And because we're going to draw all of the products, we're going to use both beta carbons. So let me show you how we would get started on this. Let's see, I'm going to number this chain just to make it easier to talk about. Let's see, I'm going to start over here for really no real reason. Okay, so it's a 5-carbon chain. There's an ethyl group attached to it. Okay. So there's the basic carbon chain. The only thing that I did different is I didn't draw in the halogen. But when we do this reaction, we know that we're going to have loss of a leaving group. So that's our bromine. And we're going to have a proton transfer, and that's coming from one of the beta carbons. And so we're going to make a new double bond between the alpha carbon and the beta carbon. That's the only thing that's happening in our product. Double bond between alpha and beta. So because we're drawing every possible product, there's my first product. I have a double bond between, I'm going to give my beta carbons numbers. We're going to call this beta carbon 1 and beta carbon 2. I have a double bond between the alpha carbon and beta carbon 2. What should my next product be?
Are we drawing in the bromine?
No, because the bromine is a leaving group. So if we want, over here on the side, we could put plus bromine minus. But in reality, if the question says we're drawing in, okay, this is not a good example. If I was going to say if it says all the products, but really, we don't care about the bromine. Just like it's also forming water because the hydroxide's grabbing onto a hydrogen, but they're over here. We don't really care about them though.
Are we going to have a double bond on the beta carbon one?
Yes. So we'll go from the alpha carbon over to beta carbon 1. There are still 2 more possible products. This is going to have 4 products possible. We only have these 2 locations though. We can go from alpha to beta 1, or we can go from alpha to beta 2. So how could we have 2 more products if we only have these 2 locations?
Maybe we have the same structure just as a cis.
That is
on
exactly
the
right.
cis position. Yeah. Okay.
Perfect. So I'm going to redraw this one. There's my double bond. And on the first one, carbon number 1 was pointing down so that it was trans. I'm now going to point it up so that it's in that cis position. So let's see. I kind of turned this into a little bit of a table here, but this is going from our alpha to beta 2. and we have the trans, and we have the cis, and this is going from alpha to beta 1, and we have the trans, so that means we need to draw, well, that one technically is not cis or trans, but we need to draw the other configuration. So here's my double bond. I had the ethyl pointing up and the methyl pointing down. I'm going to flip those. There's my ethyl, there's my methyl. So in this one, we have the E and the Z. So at each location, you can have two possible stereochemistry outcomes, because you could have cis and trans, or E and Z, depending on what your substituents are. So this is everything. This is all of our products. So if you're trying to figure out how many possible products there are, however many beta carbons you have, times 2. Let me put that up at the top here. Number of possible, I need to move my zoom controls. Number of possible products equals the number of beta carbons times 2. And it's times 2 because at each beta carbon, we could have cis and trans, or E and Z. So in this one, we had 2 beta carbons and we had 4 possible products. Now, I said number of possible products because if you have, let me go back to our original example. Yeah, that's not what I really wanted. So this one, for example, there's 3 beta carbons, but there's not 6 products here. There's only 1 product. One of the reasons is because of symmetry. So if we drew a double bond to any of those beta carbons, it would be the exact same product. The other reason is this doesn't have a stereochemistry label. This is not cis, trans, or E or Z, and it's because one side has 2 hydrogens attached to it. So we can't say which side has a higher priority. Or another way to think about that is if you flipped those 2, it would still be the exact same thing. So I am giving you a little bit of a flashcard answer here by saying number of possible products is beta carbons times 2. But you just got to take that with understanding that that's going to go down if there's symmetry. It's going to go down if our alkene is at the end of a chain. So it'll help get you in the right direction, but it's not going to necessarily be the last answer, if that makes sense.
Is there a way to determine how many possible products, or are you gonna tell us just find them all, or will you tell us like, oh, this one has 4 and find them all?
So that's what this is up here.
Oh, okay. Okay.
So I will not tell you how many there are, because that will be part of what you have to figure out. All right, the second half of this question, though, is asking us to circle the major product. So we have 4 to choose from here. Out of these 4, which one is going to be the most stable? So major product, we know that that means it's going to be, it's going to be our most stable alkene, which means, well, I don't want to say what it means. We'll figure that out as we go through it. Let me give these some numbers. 1, 2, 3, or 4. Which one of those? I agree. That's our major product. Why is that our major product?
Because the biggest groups are on the opposite sides.
Yes. So that's one reason. There's one more reason. Anyone know what the other one is? If we compared 1 and 2 versus 3 and 4, what puts 3 and 4 more stable than 1 and 2? They have more substituents. So this one's our major product because it's tri-substituted. Oh, I'm almost ran out of room there. And the big groups are opposite from one another. So let me give it a couple labels to show you what I mean there. So when we say it's tri-substituted, 1, 2, 3, it has 3 substituents coming off of the double bond. Number 3 is also tri-substituted. So if we were ranking these, this would be the next most stable. But number 3 has the big groups on the same side. And so the big group is the ethyl and the ethyl. So on number 4, they're opposites from each other. But on number 3, they're on the same side of as each other. So number 3 is going to be a little bit less stable than number 4 because the big groups are on the same side. Number 1 and number 2 are both di-substituted. So there's the 2 groups coming off of our, off of our double bond. So these are both di-substituted. Out of number 1 and number 2, which one of those is the more stable?
Number 1,
How come?
because the trans.
Good. So number 1 is trans, number 2 is cis. So actually, we do have enough information to fully rank these. Let me put it right here in the middle in a different color. So number 4, if we're doing most to least stable, number 4 is the most stable. And then number 3, so these are both tri-substituted, but number 4 has the big groups on the opposite side. And then number 1, and then number 2. So 1 and 2 are both di-substituted, but number 1 is trans and number 2 is cis. I know that kind of all overlapped a little bit, but I wanted to get it all up there. Questions? On any of it, where I got the products from, the rankings.
Yeah, how come Ian's, or how come number 4, I guess, would be most stable? Because in the rules, like it said that with, if it's trans, wouldn't it be the most stable? Like
So we're using the word trans kind of loosely here. So when we're saying trans, we're saying that we want to have the big groups. Oh, and I labeled E and Z backwards, didn't I? I just realized that. That's probably why you're saying that. But we want to have the big groups trans. So we want to have the big groups far away from each other. This is E, this is Z. And so in number 4, the big group on each carbon is this ethyl group, and there's a hydrogen right there. So the big groups are opposite from each other, or the big groups are trans from one another. And so that is why it ranks it a little bit higher. Does that make sense?
Yes, thank you.
Any other questions before we move to the next slide? Okay. Oh. All right. So we just talked about that the Zev is the major product. But of course, there's exceptions. So one of the things that you will, why did you change the E and the Z? Oh, let me go back a slide. Let's talk about that real quick. So I had them labeled backwards to start with. I didn't realize it till we started discussing it. But number 4 So the two groups that I have circled are, oh no, they were right, weren't they? I'm sorry, they were correct. I second guessed myself there. So yeah, Z is the same sign. Can I undo? I don't think I can undo because it's not. No, it will not. Okay, I'm sorry. I totally erased that and didn't mean to. Sorry, I totally messed you guys up on that one. Okay, so I know I totally messed up on that one, and I'm sure that's annoying. On the other side, whether it's E or Z doesn't really matter, because E and Z is ranking these based off of atomic number priority, just like we do with RNS. What we're really looking at when we're trying to decide cis and trans, major, minor for this, is we're looking at where the big groups are in relation to each other. So if you look at one of the alkenes, here's the two vinylic carbons. There's the big group on the carbon on the left. There's the big group on the carbon on the right. Are they on opposite sides or are they on the same sides? So whether we would officially label that as cis, trans, E, or Z isn't actually important in this case. So yes, I'm sorry. That was annoying that I messed that up more than once. It doesn't come into play in terms of deciding our answer for this though. Okay. Let's move on. So there's exceptions. I had an OChem class years ago that they said that the tagline for OChem should be, but wait, there's more. Because every time you learn about a reaction, then you have to learn about like the exceptions to the reaction or the side rules that go along with the reaction. It's never just those first couple slides. There's always a couple extra. So here's our exceptions. So this is still E2. These are exceptions to the regioselectivity. So remember, our regioselectivity says that the more substituted alkene will be our major product. Or another way to say that is that the Zaitsev product will be our major product. If we use what's considered to be a bulky base, then our major product will be the Hoffman product, or the one that is less substituted. So Hoffman is the less substituted product. The reason for this, steric hindrance, our go-to reasoning. So as that base goes to the beta carbon to remove that hydrogen, if the base itself is really big, then it's going to go to the carbon that has less substituents because there will be less stuff in the way. And so it might not be making the most stable alkene, but during the reaction, it went to the more accessible hydrogen. So we're going to look at the table down below, and then we'll talk about some of those bases up at the top. But we have our starting alkane there. So we have 2-bromo, 2-methyl butane. We're reacting it with a base. And so we have our list of possible bases. And so there's two possible products for this reaction. Here's our alpha carbon right there in the middle. Oh, that was weird. And there's technically 3 beta carbons. Beta, beta, and then this one up here is also a beta, but because both of the beta carbons on the left side, they're both methyls, it would give us the exact same product. So because it's the same substituent type, it's going to be the same product, so we don't need to list it twice. So if we go to the beta carbon on the right-hand side, we get the Zaitsev product. So this is going to the beta on the right. If we go to the beta on the left-hand side, we get the Hoffman product. So what we just learned is that the Zaitsev product is the more stable alkene. It's tri-substituted in this case. The Hoffman product is the less substituted alkene. It is di-substituted. It only has 2 substituents coming off of it. And if we use a base like ethoxide, so that's an ethyl group with a negatively charged oxygen. So we'll use those names a lot. So we're using, I think I used methoxide earlier. We're using the prefix for however many carbons, so meth, eth, prop, whatever it might be. And then when it's a negatively charged oxygen, we're using oxide. So it's not a name that you need to know for the test, but it's definitely a name that you'll see in the book and a name that I will utilize as I'm talking about them. All right, if we look at the percentages, when we use ethoxide, the Zaitsev is our major product. 71% of the product is the Zaitsev and 29% is the Hoffman. So the majority, the major product, is the Zaitsev. If we switch to this guy, so this is tert butoxide. Actually, let's spell it out. The percentages almost flip compared to our first one. So now our major product is the Hoffman. 72% of our product is the Hoffman and 28% is the Zaitsev. And then that last one, that guy doesn't even get a name. Well, he would, but not like an easy name. This one kind of looks like a sea creature or something you'd see in biology is like a neuron or something. Notice how drastic the percentages are now. So the Hoffman is still our major product, but by even more. And so what's happening as we're going down that chart is our base is getting larger. And the word that we use for this is bulky. For some reason, that's just the word that we utilize to describe these. But as we're going down that chart, we're saying that the base is getting bulkier and bulkier. And as we have a bulky base, the Hoffman product becomes our major product. The top of the slide is showing us the most common bulky bases. So the first one is potassium tert butoxide. So we know that the potassium is just the counter ion. It could be sodium tert butoxide, but that's not the part we care about. We care about that negatively charged oxygen with the carbons attached to it. So seeing it written like this is how you'll probably see it written above an arrow. It might also be written without the potassium, or it might have sodium in its place instead. But it's that tert butyl group with the oxygen attached is the part that we care about. The other two that are up there, we have diisopropylamine. So we have our amine in there in the center, our nitrogen, diisopropyl, so 2 isopropyl group attached to it. So the nitrogen is the base portion, and then we have those isopropyl groups that make it bulky. And then the last one is triethylamine. So again, we have the nitrogen, the amine, and then 3 ethyl groups. This one gets used enough that it has its own abbreviation. T. So triethylamine. If you're making a reaction notebook, if you're making an acronym list, Definitely one to add to it. We will see it often enough. I'm going to do a practice one for us on the next slide. Before we do that, though, are there any questions? Okay. Oh. Okay. I have some practice ones for that slide, too. We'll do them one at a time, though. Whoops. Let's try that again. Okay, so we have an alkyl group with an iodine attached to it in the center, and we're going to react it with two different bases. So on the left, we're reacting it with sodium hydroxide, and we have a space there to draw in the major product only. And on the right, we're reacting it with tert butoxide, potassium tert butoxide. And again, we're going to draw in just the major product. So as we're looking at this, we have to decide a couple things. We are talking about an E2 reaction here. We know that because it's an alkyl halide. We know that because we're reacting it with a base. Later on in the chapter, we'll add some extra reasoning to that and some decisions to that, but that's where we're at right now, which means we know we're going to form an alkene between the alpha and the beta carbons. So if we look at what we're starting with, there's the alpha, right where that halogen is attached. We have, how many beta carbons do we have attached to our alpha carbon?
3.
We do have 3. Beta 1, beta 2, beta 3. So our decision then, when we're drawing in our major product for each of these, is where's that double bond going to go? Is it going to go to 1, 2, or 3? Should we draw it as a cis or trans, an E or Z? So we have regio decisions. The regio decision is which beta carbon do we go to? And we have stereo decisions. The stereo decision is cis, trans, E, or Z. So let's talk about the left side first. We're going to talk about the sodium hydroxide product. Which beta carbon is our double bond going to go to?
3.
It is going to go to 3. What about stereochemistry? How about this? Did I draw the right stereochemistry product?
Yes.
Yeah. Is there more than one though?
Yes.
Oh, there isn't in this case. So the reason why, because this side has 2 methyls on it. So we can always think of it as if we took those 2 substituents on one of those carbons and we switched their locations, would it switch it from E to Z or cis to trans? And because they're the same, it wouldn't make a difference. So there's only one stereo outcome for this reaction. So we put it onto beta carbon number 3 as our regio option. Would we label this as the Zaitsev product or the Hoffman product?
Zaitsev.
It is the Zaitsev. And it's the Zaitsev because it's the more substituted option. What about the other side? So what about if we react it with our tert butoxide? Which beta carbon are we going to draw our double bond going to?
Number 1.
Yes.
Would we ever draw the double bond for number 2?
So having our double bond go to beta carbon 1 or 2 is actually the exact same thing. They might look a little bit different when we draw them, but those are technically the same product. One way to see it, if I fill in some hydrogens here, so if we look at this vinylic carbon has 2 hydrogens attached to it, and this one has a methyl and a propyl. This carbon has 2 hydrogens attached to it, and this carbon has a methyl and a propyl. So going to either carbon 1 or carbon 2 is going to give us the exact same product. Let me erase this one. So this one is going to beta 1 or 2. This one went to beta 3. Well, I know I'm not going to be able to erase just the blue there. I'll erase that. This is our Hoffman product because it's less substituted. And again, just to kind of emphasize what that means, there's 2 carbon substituents coming off of the double bond. On our Zev over here, we have 1, 2, 3 carbons coming off of our double bond. So this is tri-substituted. This is di-substituted. So why do these 2 have different major products, these different bases? What makes that tert butoxide have Hoffman as its major product? What's the word that we would use to describe it?
It has like a bulkier base.
Yeah, this is a bulky base. And so because it's a bulky base, we're going to go to the less substituted side. We're going to form that Hoffman as our major product. And so this is a good thing, because if we want to make this as our product, we know we can use a bulky base to get there. If we want to make the other one as our major product, we can use a smaller base to get there. So we can force that double bond to form on either side, depending on which reagent, which size of reagent we use. Questions at all about this?
The bulkier base would come from what we're trying to react it with. So like in this case, it was that tert butyl.
Yes. So this and this are our bases, and that's what we're deciding if they're small or if they're bulky. And our divider line, because I know this is going to come up, especially as you start to do practice problems. Ethoxide is the last small base. So what I mean by that is if we have hydroxide, methoxide, ethoxide, those would all be considered small bases. But then if we put a propyl group on there, propoxide, propoxide, I don't know. It's used so little that even sounds weird. But really anything bigger than an ethyl group is going to be considered to be a bulky base. Now, most of the time, we're not going to use something that's like questionable, like a propoxide. And I say it's questionable because it's kind of on the border of being a small versus a big. Normally, we're trying to be very, very obvious. So in this case, we have a very small base, hydroxide. It's about as small as we can get. And we have a very big base, a tert butyl group. So we're trying to be very obvious because we don't really want to get a mixture of both products. So kind of a weird little side note there, but that always comes up later on as you're actually doing problems and thinking about it, is where's that divider line between bulky and not bulky? Okay, any other questions on this? Checking our time here. Okay. We're doing okay. Oh, wait, I skipped a slide. We got to go back here. We talked about regioselectivity. The other half of this section is the stereochemistry. So we talked about cis versus trans, cis, and we talked about trans as major. We even talked about Y already. We talked about the steric hindrance. So a reaction like this is a stereoselective reaction. That means that more than one stereoisomer can form, but one of them will be the major product. So the cis and the trans are both capable of forming. The trans will be the one that we have a bigger quantity of. This can also be a stereospecific reaction. So a stereospecific reaction is when the stereochemistry of our products depends on the stereochemistry of our substrate. So we saw this with SN2. SN2 is stereospecific because if our starting material is R, it goes through an inversion so that our product is now S. So it depended on that starting spot. This is a very specific example when we're looking at E2. It's only going to matter if there's only one beta hydrogen. So this is a very specific example that doesn't happen very often. But the reason why it's going to happen when there's only one beta hydrogen is this last bullet point. It says that the hydrogen and the leaving group need to be anti-coplanar. So there's a little bit of a 3D picture down here to kind of explain what anti-coplanar means. So coplanar means that they're in the same plane. So meaning the hydrogen, both carbons, so the ones that are going to become vinylic carbons, the ones that, well, the alpha and the beta carbons, the ones that will be part of the double bond, and the leaving group all have to be in a flat plane. So notice the way it's drawn here. I'm going to, let's see, get a color that'll stand out a little better. This bond, and this bond are all drawn as lines. So meaning they're flat with the screen, they're flat with the page. The other ones, the methyls, the C6H5, which is a benzene ring, the other hydrogen, those are dashes and wedges. So those are coming out at you, going away from you. But the hydrogen and the bromine are in the same plane. They're coplanar. The other half of that word says that they're anti. So that means that the hydrogen has to be pointing in one direction and the leaving group has to be pointing in another. So they're opposites from each other, but in the same plane. Here's why it has to be that way. So we'll leave the blue there. If we look at the mechanism arrows, so I'm just going to draw on top of them with red. Here's my base up here. The base is grabbing onto that hydrogen. We're using those electrons to form our double bond, and the leaving group is taking off. The base and the leaving group are both going to be electronegative, partially negative, fully negative. They're going to repel each other. So as the base is coming in, that leaving group needs to be far away from it to allow the reaction to happen. So that's why they need to be anti. They need to be on the same plane so that the p orbital that is going to form the double bond between those two carbons are lined up correctly. So a pi bond has to have that side-to-side overlap. When the bromine leaves, it's making an orbital available. When the hydrogen leaves, it's making an orbital available. So they have to be in the same plane to make those orbitals that are now open match up correctly. Here's what it means for the product. When we remove that hydrogen, we remove that leaving group, the rest of the substituents have to stay in that same position. So notice that the methyls are both on dashes. So the methyls are going to be on the same side of that double bond. And the C6H5, which is a benzene ring, and the hydrogen are both on wedges. They're on the same side of the double bond. So having that hydrogen and that leaving group in that anti-coplanar configuration means that the rest of the groups are locked into place. So this might not be the most stable alkene possible, but it's the only one that can form because of the need for that certain shape to have happen. All right, we're going to practice this. And one of the easiest ways to see this is in a ring. Let's see, do I have one more picture for this? No, okay. I do need to add in an extra blank slide though. Let's do that first. Okay, so I'm going to draw I'm going to draw our starting material there. So we have a ring, we have an ethyl on a wedge, we have a chlorine on a wedge, we have a methyl on a dash, and we're reacting it with hydroxide as our base. And we're going to draw the product for this. So we know with an E2 reaction that we're going to form a double bond between our alpha carbon and our beta carbon. There's my alpha. I have a beta on that top carbon. I have a beta over here on the right. We have to decide if both of those are going to be possible or if only one is. If they're both possible, is one major, is one minor? And we're obviously using our information we just learned on the last slide. So I'm going to redraw this, but include all of the hydrogens that aren't shown, because we know that one of the hydrogens has to get removed. Not going to put the hydrogen on the alpha carbon because that's not getting reacted. Okay. So we know that our leaving group is leaving. And it's drawn on a wedge. If our leaving group and our hydrogen have to be anti from one another, what do you think our hydrogen has to look like? What type of bond should it have in order for them to be anti from one another?
Anti to the chlorine?
Mm-hmm. So should our hydrogen be on a dash or a wedge that we want to remove?
The wedge.
So it's actually going to be the dash because we want it to be opposite from the chlorine. So we want them to be far away from each other so that our base and our chlorine aren't repelling each other, and it allows those double bonds to form correctly. So if we look at our options here.
What do you mean by opposite? You mean by like opposite from a wedge?
Yeah.
Okay.
Yeah, we want them to be pointing away from each other. So in this case, because the chlorine's on a wedge, we want our hydrogen to be on a dash to be pointing away from it. So our double bond is going to go to the beta carbon that's in that top position because that's our hydrogen that is anti-coplanar or opposite from our chlorine. The hydrogen that's on the bottom is what we would say syn coplanar, meaning it's pointing in the same direction as our chlorine. And so we can't do that reaction. It's not going to form. So our final product when we react this with our base, down here we still have that methyl on a wedge. There's our new double bond, and there's our ethyl group. When we have a double bond, that ethyl is no longer on a wedge because the carbon in the double bond is now trigonal planar. We only use dashes and wedges for tetrahedral carbons. If you put it as a wedge on the test, I wouldn't mark you down. I might cross it off, but unless it's going to make your answer wrong, I wouldn't care. But just a little side note there. This is the only product. If it's the only product, we wouldn't label it as major. We only use the term major and minor if there's two or more possible products, and we're saying that one of them is forming in a larger quantity. If it's only one product, then major is not really quite the right description for it. Questions about that, though? Okay. I think this was our last E2 slide. It was. So that means we're moving on to our other two reactions. And we're going to start with SN1. So we've done SN2 and E2. The other ones are SN1 and E1. So we kind of know what that stands for. SN1, the S is substitution, the N is nucleophilic, and then the 1 stands for unimolecular. Or another way to think about that is only one thing is going to happen at a time. So when we did an SN2 reaction, we had a loss of a leaving group, we had a nucleophilic attack. The same thing is going to happen here, but it's going to happen one step at a time. So here's our reaction up here at the top. We have our substrate. So we have an alkyl group that has a leaving group attached to it. We're going to react it with a nucleophile. And then we get our substrate with the nucleophile attached to it, and then our leaving group. So what's happening in the reaction is the exact same as the SN2. The nucleophile and the leaving group are switching places. The leaving group's going to be on its own. The nucleophile is going to bond to that carbon group. How it's happening is where the difference is, though. So we have our mechanism down here. Step number 1, loss of a leaving group. So there's our arrow. Oh, moved my tablet right as I was trying to draw that. Step number 1, loss of a leaving group. Now notice here it tells us that this is the slow step. The reason why this is the slow step is because we're forming a carbocation. Carbocations are not stable, they're not happy. So this is the reaction that's going to have the big hill in our reaction diagram. So here's our carbocation, and here's step number 2. Nucleophilic attack. Our nucleophile is going to bond to that carbocation. Now, when we do an SN1 reaction, a lot of the times, not all of the time, but a lot of the time, we're going to have a neutral nucleophile. When we did SN2 reactions, most of the time, we have a negatively charged nucleophile. Because we're going to use a neutral nucleophile a lot of the time, that means that we're going to need a third step. And the third step is right here. We're going to do a proton transfer because after that neutral nucleophile adds, it's now going to be positively charged. So we're using water as our nucleophile. It's going to bond to that carbocation, but now the oxygen has a positive charge. It has too many hydrogens attached to it. So we're just going to use another water molecule to grab onto that hydrogen so that we end up with our final product over here without any charges on it. And then the water ends up as a hydronium, ends up with that charge, but our final product is neutral. So down here at the bottom, we have some bullet point information. We're forming a carbocation intermediate. Now, I said that, I pointed it out. This is our slow step. One of the reasons why it's mentioned here, though, when we learned about our mechanism patterns, one of the things we learned about were carbocation rearrangements. So because we're forming a carbocation intermediate, we're going to have to look out for possible carbocation rearrangements. Let's see, we talked about that. Let's talk about this one right here. This reaction is called a Silvolysis reaction, which is a hard word for me to say even though I say it all the time. What that means is that the solvent is the nucleophile. So when we talked about SN2, we talked about the different types of solvents, and we talked about that a polar A product solvent is going to work best. With an SN1 reaction, we actually are just going to have a solvent, and the solvent is going to be our nucleophile. So it's going to do two jobs for us. And that's also why right here, when we're using water to remove that extra hydrogen, that's one of the reasons why, because the water can do two jobs. It can be the nucleophile, and then it can act as the base to remove any extra hydrogens. All right, last bullet point I want to point out here. We're going to form a racemic mixture. So when we talked about stereochemistry of SN2, we said that it goes through an inversion. If our leaving group was on a wedge, our nucleophile would be on a dash. This one's going to be racemic because we form that carbocation. So once we have that carbocation, it's trigonal planar. Our nucleophile can attack from the front and be in a wedge position, or attack from the back and be in a dashed position. Now notice it does say racemic in quotes. Racemic is technically a 50-50 mixture. It's not going to be a perfect 50-50 mixture, and I don't think we're going, unless it's the next slide. Oh, it is the next slide. Okay, we'll talk about that now. Questions on this slide before we move to the next one? Okay, so let's talk about that racemic mixture part. So here's the racemic portion up here. Here's our very, very generic substrate. So it's a carbon with some R groups attached to it. Notice they have the little tick mark. So there's one tick mark and two tick marks. It's just saying that they're different things. So it's just a way to be super generic, but also a way to say they're not the same as each other. We have a bromine leaving group in a wedged position. We're reacting it with our water. So there's our nucleophile. And then we're forming two products, two stereochemically different products. So this one has the same stereochemistry as what we started with. I know that because of the way it's drawn, the way that it's shaped. So our bromine is on a wedge and it's pointing to the right. We could also draw this. Let's see, that's not a good spot to draw that. If I put my bromine there. Oh, I had to move my zoom controls. I could say that these are my two products. And the one with the wedge, we would say has the same stereochemistry as what we started with, or it has retained stereochemistry. And then the other one has inverted stereochemistry, or the opposite from what we started with. We will get a mixture of both. The product that has the inverted stereochemistry is going to be in a little bit higher of a concentration. The reason why is as that leaving group is leaving, the nucleophile is already ready to do its attack. And so the backside, where the inverted stereochemistry is going to come from, is going to be available faster than the front side. So if we're thinking of speed of reaction, that bromine doesn't get out of the way fast enough in order for the front side to be available. So really, this just tells us that the inverted stereochemistry is going to be in a little bit higher concentration, but we still label it as being racemic because they're super close to each other. All right, we are totally at time. We'll come back to this and kind of start here just to see if there's any questions on, oh my gosh, I'm not going to see you guys in lecture forever. Wednesday's a holiday. Wednesday's Cesar Chavez Day, so no school. Next week is spring break. So 2 weeks from today, we will continue this chapter and hopefully finish this chapter. But we are going to have a little lab lecture today. So I'll hang out here just in case there's any last minute questions, but go click on that lab link and we will chat about our experiment for today.
Thank you.
Thank you, guys.
Thank you.
Any questions from the few of you that are left there?
Yeah, I had a quick question.
Yeah.
On like this top reaction right here, how come when the water nucleophiles with this compound, it only gives one hydrogen and not both?
So I'm not sure if I understand what you mean. What do you mean it only gives?
Like it starts with
100?
H2O in the beginning and then the product is HBr. So like it's just OH on the bottom, not CH2, or sorry, not CH2O, like
So
H2O.
So you kind of answered your own question, actually. So we have H2O, so we could think of it as a hydrogen and a hydroxide. The hydroxide goes to the carbon, the hydrogen goes to the bromine. So we're splitting that water in half.
Okay, okay.
The way that it happens is that, so down here, the water, the entire water molecule does bond to the carbon at first.
Oh, and then there's a proton transfer.
Yeah,
right
and
here.
then we take off that extra hydrogen to make it back to neutral. So
Got
if
it,
we
got
were
it.
just asked what is the product, we would draw it like this. We wouldn't need to draw that extra hydrogen on there at any point. If you're asked for the mechanism, then you would need to draw this whole thing where you're showing how each step happens.
Okay,
Okay,
that makes sense. Thank you.
you're welcome. Oh, thank you, Emma.
Information. No problem. Yeah,
Okay.
hopefully it helps out.
Yeah, let me copy and paste that, put that somewhere else.
All right. Thank you, Professor. See you.
Thank you.
Bye-bye.
All right, where did Zoom go? Sophia, any questions before I log off? Okay.